In the previous lecture, I tried to explain why we use momentum, what purpose it serves for us that something like forces or energy don't. And it turns out that momentum is actually very intimately related to both forces and energy, and primarily to forces. We know Newton's second law as the sum of forces equals m times a, and I should have vector symbols over those as well. But in reality, when Newton first came up with Newton's second law, he didn't talk about it exclusively in terms of mass and acceleration. He talked about it as the sum of forces being equal to the change in the quantity of motion of the object. So he had something that he called quantity of motion, which we could take to mean how much stuff is moving and how fast is it moving. That's really what quantity of motion means. And this dp dt, that's just the rate of change of this quantity of motion. It can also be written like this, and this is how we'll write it in this class, is the sum of forces equals the change in the quantity of motion divided by time. There's no difference between quantity of motion and momentum. So he was really discussing momentum. So if you want to change the momentum of an object over a period of time, you need a sum of forces. The more you want to change the motion of an object with a set amount of force, the more time you're going to need to do it. To give you an example, just a quick example here, let's say that I want to change the momentum of an object by 5, and the units for this would be kilograms meters per second. So I want to change the motion of an object by 5 kilograms meters per second, and I have a force of 5 newtons with which to do it. So that would indicate that we need a time of 1 second. On the other hand, if I wanted to change the motion by 10 kilograms meters per second with that same force of 5 newtons, it would take twice as long. That's all that he's saying. So the more you want to change the motion of an object with the same force, the more time you're going to need to do it. Or if you want to do it in the same amount of time, 10 kilograms meters per second in a total of 1 second, you'd need 10 newtons of force. The units for this change in momentum, I wrote it as 10 kilograms meters per second. It could also be 10 newton seconds, and that comes from this up here. If I just take this and rearrange it, I get change in momentum equals the sum of forces times delta t. So this would be newtons times seconds. And this term right here, we call this change in momentum but we also call it by another word, which is impulse. And impulse really gives us an indication of how rapidly the motion is changing when we multiply the force by the time. Now, as for the fundamental definition of momentum, what really is momentum, we can take it from this. So if I combine this idea, or this one right over here, they're equivalent, with m times a, we should be able to get out an explanation of what the change in momentum is in terms of maybe more fundamental ideas than a sum of forces times the time. So if I set m times a equal to change in momentum divided by time, I've rearranged this and I get mass times acceleration times time equals the change in momentum. Well, this acceleration is nothing more than mass times change in velocity divided by the change in time times the change in time equals the change in momentum. So I can cancel out these times, and I wind up with the change in momentum equals mass times change in velocity. And if that's the change in momentum, then that seems to indicate that the actual momentum of an object is equal to its mass times its velocity. Okay, and this is the fundamental definition for momentum. Why we use p for it, I'm not sure. No idea. No idea at all. But we use p for it, and that's the way that it is. It is a lowercase p. It's not a rho, even though I kind of made that one look like a rho. And it's just equal to how much mass there is times how much velocity there is. Now, how is this useful to us? And how is this different from, say, kinetic energy, where kinetic energy is equal to 1/2 mv squared? Very similar ideas, okay? Or how is it different from force, which is m times a? And these are important differences. The m times a one is pretty easy to tackle because I did it right here. So how is momentum different from m times a? Well, it kind of goes back to this. This is equal to m times a. If you want to accelerate an object, or if you can accelerate an object for a certain period of time, it's going to change the velocity by the same amount. If you cancel out mass from this and mass from your sum of forces equation, you just get that the acceleration times time equals the change in the velocity. So that relationship is actually pretty straightforward. Forces cause changes in momentum. The longer the force is being applied, the greater the change in momentum that occurs. The larger the force that's applied, the greater the change in momentum that occurs. So that's a pretty fundamental idea. This one is one that we'll tackle in a future lecture, because it is a little bit trickier to see how these two things are different. What I'm going to do next is focus a little bit more on this idea of impulse and change in momentum and the relationship with forces. Okay, so on the previous slide, I had talked about this change in momentum or impulse idea being equal to the sum of forces times the change in time. This is a pretty fundamental idea, and we can see it applied in a case where we have two objects colliding with each other. So this is, let's call this M1 and this one M2, and they're going right towards each other. It's going to be messy. They're going to bounce off of each other in a time that's very, very small. To give you an idea, maybe let's say that this from right here, this is 1 millisecond, and this is 3 milliseconds. So it's taking place over the course of 2 milliseconds. Very, very tight time frame. We're not likely to be able to detect what's really taking place inside of there. But let's say that you did. Let's say that you had a really precise instrument that was able to measure the forces. I set up something like on this one where I measure the forces on it. This is an accelerometer or something. What's going to happen then is, if I look at this, just by looking at this force and time diagram, I should be able, by taking the area underneath this curve, I should be able to figure out what the impulse is, because this gives me my force times time. So we are going to be doing experiments where we're trying to capture this, and we're going to be honestly trying to slow down the collision as much as possible so that we can get this as accurately as we can. And in doing so, we should be able to monitor what the change in momentum is for a particular object, and use that to try to help us see whether the trial is valid or not. But also just to get a better feel for how long is the time frame taking place if you have an object and it stops in two cases. So let's say that we have these two objects, and this one was initially going forward, and then its final velocity ends up being 0 after the collision occurs. So there are multiple ways that could take place. One way is, of course, that it could go like this, but it's also possible that you could have a collision that extends over a much larger period of time. So you could have something like comes up and it gradually makes its way up and then gradually makes its way back down. And so the area under these curves might be exactly identical, but the actual nature of the collision was very different. So this one was a very short, fast collision with high forces involved. This one was a more drawn-out collision with lesser forces involved. So this, if you're a passenger in this vehicle, say this is probably the collision that you want to have, because it's a little bit drawn out. This is going to be lesser forces, lesser accelerations. Overall, most likely, the safer of the collisions. And a lot of safety devices are intended for no other purpose than to extend the time of the collision, to reduce the force, because they're assuming that this isn't going to change very much. If you hit another car and you come to a stop in the collision, there's nothing they can do about this. This is an initial to a final state. This is non-negotiable, at least in this particular case. It's non-negotiable. We're moving at a certain speed. We're going to stop. So this change in momentum will be the same no matter what actually takes place during the course of the collision. However, we can control this And as a result, we can control this one. And that's evident in this example below. Now, just to wrap up, we talked about what momentum is. Momentum is m times v, and it measures the quantity of motion. It's a reference to 0. So what that means is that if you have 10 kilograms meters per second, that really tells you how much stuff there is in motion and how much stuff there is that you need to stop then as well, and how hard it's going to be to stop. It is also a vector. It has direction. So you can have negative 10 kilograms meters per second, or you could have positive 10 kilograms meters per second. And the importance of this direction, or this sign, is in the direction of the force that's needed to bring it to rest. So if you have an object with negative 10 kilograms meters per second worth of momentum, you need a force that's in the positive direction to stop it. Say 10 newtons over 1 second would stop it. On the other hand, if you have an object with a plus 10 kilograms meters per second momentum, then it's going to require a negative force, say of 5 newtons for 2 seconds, in order to bring it to rest. And then the rest of the lecture was devoted to this idea of impulse or change in momentum equaling the change in force times time, and how we can manipulate the maximum force that occurs during this collision by changing the time frame over which the collision occurs.